Hello, my name is Sarah Black, and this is my presentation on predicting trends in greenhouse gases for the Data Science Practicum 1. So we're going to start with going through a little bit of the background information on greenhouse gases, really what they are, and then move into why it's so important that we study them and predict their trends. We'll go through a little bit of how the data looks and any data cleaning that was done, move straight into the analysis plan, which will lead into the results of said analysis, and then we'll conclude with any future efforts. So we'll start with what greenhouse gases are, and at a very basic level, greenhouse gases trap heat in the Earth's atmosphere. So what that means is when a gas is released, it rises up into the Earth's ozone, and that ozone layer will either absorb or bounce that gas back into the Earth. If it is absorbed, it goes away. If it is not, it is bounced back to the Earth, which will cause the Earth to heat up because this gas level will just keep getting bigger and bigger and bigger. There are several gases that are naturally emitted, carbon dioxide being one of them, which is why the majority of carbon dioxide gas is absorbed by the ozone. However, there are also several gases that increase based on human activities, such as industry, farming, transportation, and even our day-to-day living, driving cars, that sort of stuff. And those gases are typically carbon dioxide and methane being our most common, nitrous oxide being our third, and then our fluorinated gases. And fluorinated gases are a composition of several gases actually that are sort of the most harmful, typically emitted by nuclear power plants, and these gases cannot be absorbed. When they are emitted, they stay in the atmosphere and can never go away. So, unlike carbon dioxide that will absorb over time, the fluorinated gases will not. They are not emitted as rapidly or as frequently as carbon dioxide, but they're also more potent and harmful. So all this leads to the concentration of these gases really affect how our atmosphere heats and cools. So more gases, more heating, less gases, less heating, obviously. So that kind of leads us to why it's so important for us to really analyze the trends and do any predictions with these gases, and it's solely to understand how it's affecting our Earth in the future. So whether or not we're going to have Antarctica, snow, oceans, water, that sort of information can all be gleaned from how much greenhouse gases are being emitted and whether or not they're being absorbed as quickly or as rapidly, or if the emission rates are just constantly building and building and building and building, causing more and more heating to occur. So all that being said, that leads us to our primary goal of understanding how these gases are really changing over time. And to really address that goal, we're looking into couple questions that focus on: are emissions increasing or decreasing, constantly increasing? Are they increasing or decreasing over time? Are there any influencing factors that cause increasing or decreasing? And can we predict any sort of trends based on the gases, the recorded data on the gases? So let's take a look at our data that we used. We used one primary data source that collected emissions from 1990 to 2012. It organizes them by country or area of origin, then your year, and then lists all of your gases by gigograms. So our little snippet shows that we have CO2, methane, and N2O, which are usually our most common, and then FHC, PFC, and SF6 are the fluorinated gases. So those all together are the fluorinated gases that are of importance. So we can notice here that we have several holes in our data, especially when it comes to the fluorinated gases. However, N2O was also one that was not collected regularly for all the countries. So because of all these holes, we really wanted to get a well-rounded sample, so found a supplementary source to compare and fill in those missing gaps. So what we did was we took the original data, segregated just out Australia for every data point from 1990 to 2012, and then we took our new data and looked at just N2O for Australia from 1990 to 2015. And so we did a one-to-one comparison to see if any data point in our original data set matched a data point in the new data set. And then we also did a chart comparison, and you can see our chart comparison here. The trends are very, very different from one another. You can also see that the values collected on our y-axis are greatly different. So that led to a little bit of more analysis and some sleuthing into our data site to really understand why and what was causing such a difference in information. And it was determined that our supplementary data site records data in tones of CO2 equivalent. So what that means is they take their N2O data, transform it with respect to CO2. So everything is recorded and shown to be N2O with respect to how much CO2 exists, which can be very helpful, however, in our instance is not. Tried to find a transformation algorithm to go backwards and get the original. That was also not plausible because the website did not post their transformation algorithm, nor did they say how the data was recorded or give a unit of measure. So that led us to just review the most complete data sets to move forward with our analysis, which would be carbon dioxide, CO2, and methane. So before we started with our analysis, we wanted to get kind of an idea of what CO2 and methane looked like. And so we looked at just the histograms. We note that there is not a normal distribution for both, which is kind of a good thing for the Earth's atmosphere. We don't have a very hard concentration with, lighter occurrences on either end. So we have primarily less occurrences of emissions, less occurrences of higher emission rates. Yes, so we have less skewed histograms. So the analysis we chose to do was time series as well as hypothesis testing. And so for our time series analysis, we chose to focus on predicting trends in CO2 and methane. We wanted to also follow on with N2O and see if that was a possibility as well for analysis. And then for our hypothesis testing, we were trying to determine if the emission rates were increasing or decreasing over time. So that led to several different hypotheses to test and really sort of look into, are there any influencing factors, and are emissions sort of constant over time, or are they increasing? So that being said, looking at our time series results just for CO2, we first started with a decomposition of the time series for CO2 to sort of get an idea of what the data looked like, if there was a visible trend we could see in the charts before we went into our REMA forecasting. And so if we look at our observed, we noticed that around 1995 there was a very, very sharp drop-off. Not sure why that has occurred. I assume it has something to do with some sort of revolution, which I'm all for. I did not do my history research on that one, so that's a bummer on me. But anyway, we kind of see that after a 1995 drop-off, we have this gradual decrease, a slight increase, and then it looks to be another decrease. So that's fairly promising. So when we did our AREMA forecasting, we were able to predict this downward trend of downward, slowly increase, slowly start to decrease again within the next 5 years. We attempted to do the same thing with methane. Again, we did a decomposition of the original time series. We have this large spike at 1995 again, which is very promising. Data matches the other data. We also have a slight increase, a plateau, and then another decrease, a little bit of increase. So it's a little more unsure what that trend is going to look like and how it's going to perform with our AREMA forecasting. When we ran our AREMA forecasting model, we did note that we were returned a flat baseline. And so looked into it, tested out the transformations we did, because before all of our analysis for both CO2 and methane, We did do stationary testing as well as independence testing to make sure the time series were both in order to do our forecasting model. Adjusted the transformations for methane first to see if maybe how we transform the data that was affecting our ARIMA forecast kept getting the same result. So then we went to sort of the Google and then the data science world to see why would my forecast model not give me a straight line prediction. And there were several answers that said, oh, there's no seasonality, maybe a random noise is the problem. So we did a decomposition of the transformed data. So this is after we tested for stationality and independence, and that's what this chart is on the bottom left. And you can see that this first one, our observed data, is almost a one-to-one comparison of our random noise, the bottom one here. And that leads us to believe that the ARIMA forecasting cannot determine the difference between observed and random noise. Looked into some sort of ideas as to how to move beyond that, and there are some methods and excuse me, some methods that are moving forward that people are examining, but there are no models or fixes for that at this stature. So with that being said, we'd have to get more of our information on the methane emissions from our hypothesis testing. So going into our hypothesis testing, we started with testing if the emission rate stayed around average, around the mean. And what we were able to note is that our p-value is less than our significant rate of 0.05. So what that shows is that our emissions are not constantly around the same. They're not staying consistently around the average, which is promising based on the data we saw. We then moved on to our second hypothesis, which was really determining if there's any, if country and year are influencing factors on emissions. So we came up with the model to test the year, the country, and then the relationship between year and country for both CO2 and methane. CO2 on the left, methane on the right. So looking at just CO2, we see that our year does provide a p-value less than 0.05, as well as several of our countries do as well. Further down, since this is just a small snippet, since it lists out 60 plus countries, and 60 plus countries' relationship with the year, excuse me, there were several countries on their own that do not influence the emission rate. However, when paired with year, almost every single country-year relationship pairing does influence the emission of CO2. So we know that it's not just independent of country and year, but it's the combination of the two. And likewise, we see something very different at this stature with methane, with year not being an influencing factor, and several of our countries not being influencing factors as well. However, the majority of our year and country working relationship does provide a p-value of less than 0.05. So overall, that relationship is what is influencing our emission rates. The final hypothesis we tested was whether emission rates are increasing over time. So this was done on the time series transform data using the trend test. And so it went through and tested whether or not overall the trend of the data is increasing. So we look for CO2 on the left, that our p-value is not less than 0.05. However, for methane, it is less than 0.05. So we can reject our null for the methane emissions and say that methane rates, I think I mixed up my hypotheses here, I'm not going to. It should say that emission rates are not increasing over time. My bad, I wrote these down wrong on my slide. But, so this test, the way it's set up, is it tests whether or not emissions are constantly increasing or decreasing. versus our CO2 data, we are not able to show that emissions are decreasing consecutively over time. So that being said, to fully understand and address this question, I think it goes back to our time series analysis of that prediction line of our prediction was not always decreasing, but it had these increasing and decreasing spikes. So that leads us to a few more following on questions, which can later be done in future research. So some of the sort of concepts that I'd like to look into in the future, the first one being to compare those prediction results that we got for CO2 with the actual data, since those results were predicting from 2012, 5 years out. We should be able to get that data source from the EPA or from another site and really test if that is the way the data is observed to be, with that nice slight increase in the decreasing trend. The next future endeavor that I'd like to take on would be to investigate why the methane prediction did not show any actual increasing or decreasing trend, why it gave us a flat line, and if that is due to the fact that our hypothesis trend does predict that it is constantly decreasing over time. And then the last would be to obviously replicate this analysis for the nitrous oxide and the fluorinated gases, especially the fluorinated gases, since those are so potent and cannot be absorbed into the ozone. Monitoring and tracking those would be of the greatest interest for the global greenhouse effect. And then just to finish up with some sources, those last two sources, that middle one is the Cadwell source where all of our data has come from, and then that bottom one was the supplemental data that was recorded in tones with respect to CO2. I appreciate your attendance and paying attention to this presentation. Please let me know if you have any questions. Thank you.